Okay, cool. So a very brief introduction to myself. So I'm G. I'm a PhD student at the physics department. This is my fifth year at UCLA, and I actually taught this class last year with the same professor. The only difference is at that time the class was in person. Now we are all online. So, but I guess the content, what we will learn in this class, is the same. So this is my email, and also I hold my office hour on Thursday from 4 to 6 p.m. And I'll use the same link as our discussion. So feel free to call in during my office hour if you have questions about, you know, material in the lecture or problems of your homework or anything about discussion stuff. Just feel free to join in the office hour and we can discuss. Um, okay, so for the discussion, the purpose is to help you guys understand better about the material we will learn in the class. So feel free to stop me anytime you want, and please do ask questions if you get confused. Okay. Um, any questions so far? Okay. So since the first class is after our discussion, right? So instead of talking about technical stuff, I decided to give you guys the motivation for this class from the physics point of view. So whenever we learn something new, we should always ask ourselves why this is important and why should we learn this? I mean, for physics, this class definitely important because to understand the physics, we need to know some math tools. And I also believe this is also important for like engineer students and also other science major students. So here I will give you a very brief view for modern physics and also its relation to what we will learn in this class. Okay, so let's start. The first subject we usually learn in physics is the classical mechanics. And often we call it analytical mechanics. Maybe some of you guys are taking this class. I mean, very roughly speaking, you can regard this class like this classical mechanics as a uh, oops, formalization of Newton mechanics, right? So here we introduce some new quantities like Lagrangian, Hamiltonian, whatever. So eventually with this classical mechanics, you can tell from the name, it's classical, right? So we can use this classical mechanics to describe the classical world. Like, for example, how a particle move from one place to another under some forces. And like, for example, I guess everyone solved this problem. Like if I have a spring attached with a box, and we can solve the Newton's equation F equal to ma to figure out the position of the box as a function of time. Very easy. So this is classical mechanics, one big topic in physics. Another one is the ENM, also known as electromagnetism. So here we will learn how to describe the light or photon, which has no mass, zero mass. And the speed of the photon or the light is denoted as c, and we often call it speed of light. And here we usually learn something about special relativity. This is because the special relativity is a theory about objects with high speed, right? This speed is the maximum speed we have in the universe. Like I didn't remember the exact number. I think it's like this. I don't know. Yeah, you need to check it. So this is special relativity is what Einstein proposed like 1905. 10 years later, he also proposed the general relativity. We usually denote as GR, where we can describe the black hole stuff. By the way, this morning's news, I think everyone received it. This year's physics Nobel Prize is given to 3 physicists for their research on black hole, and one of them is from our department. Right? I'm pretty sure if Stephen Hawking were still alive, I think he would also win the prize. But yeah. So even longer is really important. Not only doing physics. Okay, so yeah, this is one big subject. Okay, so classical mechanics is a classical word, and E&M is really a like fast object moving fast. So another one is quantum mechanics, right? If you're interested in the small non-scale physics, for example, I have a solid. If you are really interested in like the behavior of the atom or the electron inside the solid, then in this case, the classical mechanics breaks down and the quantum mechanics takes over. We know that the distance between the atom is about 10 to the negative 10 meter, which is really small. So the quantum mechanics is for small length scale physics. By the way, if you take the large length scale limit, the quantum mechanics will go back to the classical mechanics. Also, usually what we learned in undergraduate about the quantum mechanics is so-called non-relativistic quantum mechanics. Meaning that the particle, the speed is small and it's kind of a generalization, like the quantum version of the classical mechanics. So there's also people also try to combine the quantum mechanics with special relativity, which is known quantum field theory, which also is a very powerful tool in modern physics and also a very important subject. And if you try to combine the quantum mechanics with the general relativity, is what we call the string theory. Of course, there are many stories. I definitely cannot cover all those topics, and I just very briefly mention this kind of a relation, and yeah, it's a very brief overview. So the last important topic is known as thermodynamics and statistical mechanics. Right. This is definitely important. Statistical mechanics. So this is used to describe the finite temperature physics. Finite temperature. So in previous, for example, in the quantum mechanics, we know there is a Schrodinger equation. And in the classical mechanics, there's a Newton's equation or Euler-Lagrangian equation, whatever. They can only describe a particle move around, stuff like that. However, if you want to describe how a ice become a water and become gas, we cannot describe such phenomenon by solving Newton's equation or Schrodinger equation. Because in this phenomenon, there is a new degrees of freedom, which is temperature. So thermodynamics and the statistical mechanics is really a theory to capture these degrees of freedom. Of course, there are two types of statistical mechanics. One is the classical statistics, whatever, statistical mechanics. Another one is quantum statistic mechanics. So statistical mechanics will always come together with the classical mechanics or quantum mechanics. So I think those four. Wait, let me see. Yeah, right. So this kind of transition between ice, water, and gas is what we know is known as phase transition, right? And yeah, to understand this kind of phase transition, we definitely need to invoke this statistical mechanics. So yeah, this is a very brief overview of the basics of modern physics. This is also what we learn in undergrad physics class, right? So what's the relation? So what's the relation to our class? I mean, so to understand this kind of physics, there you should know some very basic math, like calculus. You need to know how to do integral. And also how to take derivatives. I'm pretty sure you know how to do it. And we also will learn in this class about like surface integral and volume integral, and also like Gauss's law, Stokes theorem, stuff like that, to help you to understand better. And we also need to know how to, okay, here's and another. We also need to know how to solve differential equations. For example, so in the classical mechanics, there's so-called Euler-Lagrangian equation. So, or you can think of this is a fancy version of Newton's equation. So in the ENM, we know we need to solve Maxwell equation with different boundary conditions. Very complicated, actually. What's Maxwell equation is? Del E equal to rho, the charge density, and the curl of E is what is, I think something like this. And the del B is 0. There's no monopole, magnetic monopole. At least we didn't discover this so far. And also the curl of this pass the current. There's some prefactors I didn't remember, but anyway, something like that. Right. For the statistical mechanics or STAMAC, whatever, STAMAC, I don't know. There's no specific equations we need to solve. Instead, it's usually, and like what I said before, it comes together with classical mechanics or quantum mechanics. In both situations, we need to calculate the partition function, right? H is the Boltzmann factor. So the trace is tracing over all the possible states. So it's kind of an integral in classical mechanics. In the quantum mechanics, is a summing over all the possible states. By the way, you don't need to understand what I'm talking here. Maybe you're learning this stuff. I just want to give you a favor, like what's going on here and what's the relation to what we will learn in this class. And so here you need to know how to do integral stuff. This is also something we learn in calculus and what something we will learn in this class. So in quantum mechanics, we know that there is an Schrodinger equation, right? I is a complex number. H bar is a Planck constant, I think. It's a real number. It's a real fixed number, and the partial T psi equal to H psi. Right? So H is the energy, is the quantum version of the energy, and psi is the wave function of whatever particle you want to describe. And of course, this is a non-relativistic version. Like many years ago, like Dirac write down the Dirac equation to describe. I'll just ignore here. You can take a look, like check on Google, whatever. And also Klein-Golden equation stuff. Everything, all the stuff, all the equations are quantum equations. And to describe most often we usually care about the Schrodinger equation in our undergraduate quantum, like solve energy levels in a potential well, whatever. You need to solve an equation. So in this class, we will learn how to solve differential equations in several different ways. And as you can see, for E and M, there are some vectors, like E, electric field and the magnetic field. And for the special relativity and also general relativity, you definitely need to know something about tensor to understand them. So vectors and tensors is also what we will learn in this class. And okay, so there's one big difference between the quantum and the classical mechanics from mathematical point of view. That is the complex numbers. You can say from the Newton mechanics, there's no complex number, like F equal to ma, meaning that you can solve all the classical problems staying in the real regime, like with real numbers, real functions. However, in the quantum like Schrodinger equation, you can say there is a explicit I factor in the equation. That's definitely one big difference between the quantum and classical, meaning that in the quantum mechanics, the complex number is unavoidable. You need to deal with complex numbers. So complex numbers and some integral stuff is also what we will learn in this class. And if you know a little bit about quantum mechanics, then you definitely know Fourier transformation is a very powerful tool to study quantum problems. So it's kind of a transform between different representations and all that you need Fourier transformation. And very loosely speaking, Laplace transformation is a special case of Fourier transformation. So all this kind of stuff I mentioned here is what we will learn in this class. Fourier transformation, complex analysis, tensors, vectors, solving differential equations, and doing integrals. Yeah, and any questions so far? Okay, I hope this gave you guys an overview of what you will learn in this class and its relation to the physics. So definitely there are some other maths you need to learn to understand them better. For example, uh, you need to know something about the probability theory, right? To understand the stomach and quantum mechanics, only a little bit. Also, linear algebra is another very important um, math tools we need to understand, I guess, like quantum mechanics. Like Hilbert space is a linear vector space, whatever, infinite dimension. And also you need something called group theory to understand the symmetry. Symmetry actually is a very important topic in modern physics, like a symmetry and symmetry breaking, to understand the conservation law in classical mechanics and in quantum mechanics. So if you know classical mechanics, there's a so-called Noether's theorem, meaning that uh, if there every conservation law is always associated with a symmetry, right? Continuous symmetry. For example, the most well-known three examples are energy conservation, which is the result of the time translation invariant of the system, and also um, momentum conservation. The total momentum of the system is conserved. Is a conserved quantity. This is because the system is translational invariant. And also the total angular momentum of the system is conserved. Is a conserved quantity is because the system is rotational invariant. And there is a precise mathematical language to describe this kind of symmetry operation. It's called group theory. So definitely you need to learn you need to know something about differential geometry and topology. To understand the what's the name? The general relativity. Very loosely speaking, what is differential geometry is just like doing calculus on arbitrary curved space. Usually we do the calculus when the calculus in the flat space Rn, right? It's yes. But what if my space is curved, like any curved space? How can can I still do integral? Can I still take derivatives? Those questions. That is the content of the differential geometry. And specifically for our GR is the so-called Riemannian geometry. Right? Yeah, topology is also another important topic to understand the global property of the system. Meaning that if you smoothly deform a system, some property of the system will robust to that deformation. It's like I think like 4 years ago, the physics Nobel Prize is given to three physicists working on topological aspect of condensed matter physics, like topological phase transition, topological waters, like that. Yeah, you can take a look. So yeah, I think this is what I prepared for today. A very brief introduction and no technical stuff, just overview. Yeah. Any questions? By the way, if you have, if you during the lecture, if you have questions, like find something make you really confused, you can email me so that I can cover that topic in the next discussion. I mean, this discussion is for you guys, so let me know your difficulties and I can help to solve. Okay, so there are like two questions. Can you explain about Rn space? Okay, Rn space is just flat space, right? So, uh, it's like a Cartesian. Any point in the Rn space can be described by a Cartesian coordinate. For example, n, so x1, xn. I, just kind of a what we learn. I mean, usually it's like R2 is a plane, and R1 is a line, and R3 is the space we have. Right? Usually people talk about R4 is equal to like R3 R. So one dimension is time, another dimension is the space. So it's space time. Yeah. Beyond that, I think it's just a mathematical construction. Yeah. What's the so yeah, I mean, so this class give you like basics you need to know to learn physics, right? For example, like all the stuff. I'm pretty sure if you know the calculus and also you know how to solve differential equations, you can understand most of the topics I mentioned here. I mean, if you want to really understand further what's going on in some specific topics, you need to know a little bit about what I said here. But that is not required, I think. You can learn this kind of stuff by yourself, reading books, or there are many online lectures you can take a note. So what's this? Okay, so for this class, can you go back to my office hour? Okay, so my office hour is Tuesday from 4 to 6 p.m. Oh, sorry, Thursday from 4 to 6 p.m. You can find the information on the CCLE webpage. If you forgot, or you can just email me. I'll try my best to, get back to you as soon as I can. And to understand the, uh, so to take the class, I don't think there any pre-knowledge you need to know. It's quite basic actually. I think the class will start with the vectors, vectors. I, I think for example velocity, I don't know speed velocity what else like what we talk about electric field and the B field stuff like that, and also some operation acting on this kind of vectors, for example divergence and the curl and yeah, that's that's quite straightforward. Uh, I don't think that's yeah. Anyway, if you feel it's difficult, we can talk together and help you. Any other questions?
I was curious about something.
Uh-huh.
What is your PhD focus?
Oh, I'm condensed matter theory. Yeah. Yeah. So like like what I said before, 4 years ago, like the Nobel Prize is given to the topological phase transition stuff. That's something relevant to my research. Yeah, not about topological stuff in my research. So this is what's why I mentioned topology. Yeah. yeah, usually people care about, for Hamiltonian, I mean, it's just a matrix, right? For Hamiltonian, usually people care about the energy levels. And we know that for metric, energy levels is just the eigenvalues of the matrix. And the eigenfunction or the eigenstate is like H, psi equal to E. And so usually people care about the energy levels because it tells the dynamics of the system. However, recently, not, I mean, it's already like 50 years, it's also relative recent. Um, People found that the eigenstate, like the eigenvalue, sorry, the eigenstate, the eigenfunction also plays a very important role. It tells you the topological structure of your system. You can construct some topological invariant quantities from this kind of a wave function stuff. Yeah, that's beyond our class. You don't need to know this. In quantum mechanics 3, I think you may, if you use the Griffith's book, there's a chapter called like Berry phase or adiabatic evolution. That's something related with the topology. Yeah. You can take a look. Griffith. Different professors taught different topics. I think like cover different things in quantum. Yeah, I also taught. I also TA'd quantum several times. But yeah, what else you guys want to know? Okay. So if no questions, that's it. I think. Yeah, we can. Yeah. Okay. You're free to go. I think.
Thank you so much.
Cool. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Thank you. Nice one. Thanks a lot.
Sure.